Session of the 1 week STTP on application of AI, IoT and nanotechnology in civil engineering. We have the next speaker with us is Dr. Uma Chaduvula. Welcome, Uma ma'am. If I introduce her, then she is right now Associate Professor at Civil Engineering Department, School of Technology, Pandit Deen Dayal Energy University, Gandhinagar. She joined as an assistant professor in civil engineering and completed her PhD in 2019 from IIT Mumbai and Monash University, Australia. She is an experimentalist and enjoys exploring science in daily tasks. She got selected in prestigious Kishore Vaigyanik Protsahan Yojana mentorship program and had worked in many institutes of importance during her undergraduate and postgraduate studies. She has published more than 15 publications, 2 design patents, and her interests are pavement geotechnics, 3D printing, ground improvement techniques like fiber reinforcement, bioenzyme stabilization, and use of geosynthetics. So welcome you, madam, once again. And now session is yours. May I request Aditya sir to give her rights to share her presentation.
Okay, thank you very much, sir, for the generous introduction. And I'll just first share my screen and I'll start. Sure. Yes, so first of all, I hope everyone is able to see my screen.
Yes, ma'am.
Okay. So thank you very much, Siddharth sir, first of all, for giving me this opportunity, and congratulations to all the organizers for this wonderful and very unique STTP, first of all, because in this time, especially post-COVID life, so this is a huge transition in our life. We want to depend on technology more than human resources, because we really don't know how our life is going to be in the future. And these technologies have really helped us to progress, and for especially in topics related to civil engineering, how we can apply not the artificial intelligence, IoT, nanotechnology. So it's actually a very wide scope and a very interdisciplinary topic. That is why I would like to congratulate the organizers for coming up with such interesting topics and organizing this session. So also I'd like to thank all the participants for joining. I hope I will be living up to the expectations. So in today's presentation, I'd like to deliver my lecture on optical fiber sensing technology in geotechnical engineering. So this work was actually done during my PhD time. My PhD was an Indo-Australian joint PhD program, in which some of the work was done in India and some of the work was done in Australia. And this work was done in Australia because my advisor, he works a lot on damage detection using this optical fiber sensing technology. And suddenly we came up with an idea, why don't we apply this in crack detection of soil itself? Because that is also a huge problem. So that is a brief outline of what I'm going to discuss today. I will be giving a presentation of close to 1 hour, 15 minutes or so. And all the questions, I'll be very happy to address the questions in the end. So you can write in the questions or whatever is the protocol followed by the STTP.
Yeah, at the end only, we entertain questions, right?
Okay, sir. Okay. So in civil engineering, particularly in geotechnical engineering, the type of failures that we see are huge, right? So let us see some of the typical failures that can be seen in geotechnical engineering. So for this, for the attendees who are not related to civil engineering, for them, geotech is nothing but which is based on earth. So every structure, most of the structure which is a civil engineering structure finds its base on the earth. So this photograph, the photograph number 1, shows a typical failure of a retaining wall. So this is a wall which is retaining this much quantity of earth. On top of it, we have a building standing, and this whole structure through a slope is retained by another wall. Now, if you look at this problem, in a typical case, unless it is the failure is because of some dynamic forces like sudden flooding or earthquake, this kind of failure has happened over a time. It means any material undergoes the stress strain behavior. All of us know about that. So this soil chunk was subjected to large amount of strains over a period of time. So this happened over a period, and this could have been avoided by a better design, or if it was not a better design, it could have been monitored because of by some instrumentation. Now let us see the picture number 2. Here also, I think this is another view of this image number 1, in which the wall which is showed here, we can clearly see the failure of this retaining wall, the retaining structure, which is holding the earth mass on top of it. We can see the failure, and we can see the strain that was mobilized in this soil structure. The third image is of a gabion wall. Gabion wall. So here what is happening? The slope was supported with this wall, and because of some additional load, this slope failed, and ultimately we are able to see the failure of this geotechnical structure. Another classic example that all of us see in these our daily lives, and especially the monsoon has passed. So we've heard a lot about the retaining structure failure due to slope instability. So slope stability is again a huge problem in geotechnical engineering. Because of rainfall, for example, the water is ingressed within the each and every pores of this soil. And all of us know that as soon as water is entering into our soil, the shear strength or the strength to resist shear failure keeps on reducing. And at a point, this strength will be overpowered by the stresses developed in the soil, and we can see catastrophic failures like this. This is one more classic example of a shear failure. So this is nothing but a wall which has undergone a failure. This failure is of the infill material. So if you look at this photograph, this is nothing but a retaining wall, and generally with the retaining walls are infilled with some kind of granular material, and here the granular material lost its stability, and there is a rupture of this wall, and there is a failure. One more classic example of geotechnical failure is the pavements. We have seen such kind of failures sometime in our life, very common. So one beauty of civil engineering is that we learn from our mistakes, and these mistakes are visible in our daily lives, right? We are able to see, even if it is a layman, he is able to see these failures in the daily life, and we are able to apply some sense, and we are able to see how these failures are going to occur. So that is the beauty of civil engineering. Here, this is another failure of a retaining structure. There is a slip of the earth chunk, which is nothing but a infill material in this retaining wall. Another example of this bluff. So these kind of bluffs you will be able to see especially in coastal regions, and coastal regions which are rocky, especially sedimentary rocks, where you'll have these kind of geological formations, and on top of it, if you have your own structure which is built on a not very much or very well stabilized soil, you can see this kind of failure. This is a rock slope failure. Here our road is passing and we can see rock which has fallen on the pavement. One of the most commonly seen pavement failures is the cracking. So here the photograph is of a rigid pavement. Rigid pavement is typically made of concrete, that is cement concrete. So all of us have seen the expressway, right? These expressways are generally made of concrete. These are the rigid pavements. And the type of cracking that we generally see is this horizontal type of cracking. And in the flexible pavements, what typically we will see the longitudinal type of cracking like this. These are the tension cracks. So these cracks, generally we try to ignore these type of crack and the vehicle will continue to ply over it. But what if the road or the soil beneath it gets washed away because of some loss in the strength or some seepage failure? There can be a huge loss or huge damage like shown in the picture on the right side. Okay. One more example are the sinkholes. Sinkholes. Sinkholes are nothing but in which the soil is washed away because of some piping failure. And one of the most affected infrastructure because of such piping failure is, first of all, pavements. And the second one are pipelines, because these pipelines are not just utility pipelines. There also be some really critical pipelines like gas, right? And if there is some leakage, in there will be a huge loss because of it. So I wanted to show in this these photographs what is the importance of damage detection. All these failures that I showed in the photograph could have been avoided. So avoided is our first aim. If we are not able to avoid it, we can at least reduce the damage. We can at least make people aware of that we are expecting some kind of failure in the structure and the loss could have been reduced. Typically, these failures occur in the region which are having problematic soil. So one of the problematic soils that is existing in our country is the expansive soils, right? So my topic, so my research work was basically for India and Australia both. So if I tell in India, the deep black soil, not just the black soil. We have some black soils in northern part of Ahmedabad also. That's a very small patch. They are not highly expansive. It's very small expansive index. But if we want to look at the deep black soils, which really have a high free swelling index, it means if you put it in water, when it comes in contact with water, it will swell. It will swell twice of its volume. So these deep black soils are shown on this map in the red. So it consists of about 20% of the land, which is also about 27% in Australia. So that is how this research works, methodology was formulated. And if I want to introduce you what happens to an expansive soil, I'd like to show this very interesting video. All of us have seen these Orbis balls at our home. So these are nothing but the balls. When they come in contact with water, all of us have seen this in our home, right? It comes in contact with water, it will swell. And if I want to measure this swelling pressure, so on top of it, you have a dial gauge, which is measuring the swell. You can see that it has gone more than 200%. The same thing, believe it or not, there are soils which will swell up to 300% of their volume. So what happens? When there is a rainfall in the right side, if you see, when there is a rainfall occurring, the soil will come in contact with water and there will be an expansion. There will be a volumetric change. So this expansion will cause a lot of pressure on our own houses, right? The soil has swelled. Now, comes the next day or next seasonal cycle. There is sun, because of which there is evaporation of water. As soon as there is evaporation, the water which was ingressed or which was held tight by this soil will evaporate. So there will be lot of shrinkage. The soil will shrink. And because of this volumetric change, there will be a formation of cracks in the soil. First of all, the soil will crack, and because of which we can expect a failure in the building. This is a very small example that I'm showing, but this kind of behavior can be related to all the failures that were shown before. So this was just a brief introduction of how we are going to relate this IoT theme of our STTP with geotechnical engineering. Now, this cracking, so first of all, desiccation, what do you mean by desiccation? It is the loss of moisture. Desiccation means loss of moisture. So because of this loss of moisture, there will be lot of cracking in the soil, which is called the desiccation cracking. And especially if I want to use this kind of soil, for example, in a landfill liner, right? So all of us know that we use material called bentonite. It's a clay material, very, very, very fine material. It is clay, right? So why we are using clay? Because we really don't want any water to percolate through this landfill lining system. All of us have seen it, right? Those who are belonging to Ahmedabad or in Gujarat, they must have heard about the Pirana landfill or any other landfill. Any city will be having some dumping area. So these dumping sites, the government, especially the Swachh Bharat mission, the Urban 2.0, which has been released very recently, the one of the most aim is to reduce this open dumping of waste. Whenever there is any dump site, we put some material beneath on which this MSW will be there. Because what happens if there is a rainfall? All this waste will get mixed up and there will be a leachate generation. And what happens if this leachate goes into our groundwater? It will be a huge problem. So first of all, such kind of desiccation cracking needs to be avoided. And there are many ways to avoid this kind of failures. One of the most commonly used method is adding some fibers into it. So the main, like for example, we have the roots. Okay, we have the roots in the grass, and the tree also has some roots in it. If there is a green cover, or if there is some trees in some area, there will not be soil erosion. Why? Because the roots will hold the soil mass and they will not allow the soil to flow away. So that was the main logic behind using these fibers. So in my study, we did experiments how to stop this cracking of soil by using these kind of geofibers. These are called geofibers because these are distributed in the geotechnical part, that is they are distributed in the soil. But as I told you that our aim was to quantify this cracking, or we wanted to see how much improvement we are able to see because of fiber reinforcement. Okay, how if I'm taking a plain soil, unreinforced soil which is having no fibers into it, and if I want to compare this cracking with fiber reinforced soil, how much difference is there? So one of the most common methods that is used is using digital image analysis. Okay, digital imaging. I can take photographs of my cracking specimen and I can quantify how much cracking has occurred. But this is superficial. Okay, from the top only I can measure how much cracking has been occurring. But if I want to see this strain development before cracking, or if I want to identify that, okay, there may be a crack which is happening before the cracking itself, like damage detection before failure, I have to measure in the material itself what is going on. So one of the method that is widely used these days is called the distributed optical fiber sensing, right? So what does this distributed optical fiber sensing does? All of us know how do we get our like for the TV cable or the telephone cable, most of it are optical fibers. So optical fibers are very commonly used for any kind of signal transmission. So this thing is also based on the same concept. We are using the same optical fiber. Optical means it is using light wave as a source, right? So here on top of it, please look at this image in which here our optical fiber is there. So the optical fiber will have a coating on it, which is called cladding. And there will be a sender, or you can say a source, which will release the light wave at a particular angle, right? And because of the light wave, and since this is an optical fiber, generally it is a glass fiber. So what is happening? The light will be reflected and then this light will be received at some end. Now look at the second image, right? So in second image, what is here? There is light frequency, and on top of it you have this light power, and in third dimension we are having the distance. So if you look at it, what is happening? We are sending a light source, and this light source is getting detected at the end of that distance. Here you have sent so this is your optical fiber, which is laid through some distance, right? So in a classic example, when there was no change, right? You have laid your fiber, it is sitting idle in some location, there is no change in, so there is no force on the optical fiber whatsoever. What will happen? There will be just a plain reflection of this light source, and there will the change in the angle of this reflection will be zero. But let us consider case number 2, in which there is some rise, so there is some load on that region. Okay, because of which what will happen is that, so if this is your optical fiber, right, this is your optical fiber, there is some load on it, because of which what will happen, there will be a minute change in the dimension of this optical fiber. Because of this change in the optical fiber, the angle at which this light wave is getting reflected, that will also change. And this change in the angle at which it is getting reflected is received by the receiver, and we will do a lot of Laplace transform, and ultimately we can come up with a strain that was generated in the optical fiber first, and from that we can tell how much strain was generated in that material, and here the material is soil. I hope everyone was able to understand. So basically this is based on this equation, in which we are seeing the change in the velocity, change in the frequency of this light wave, right? And which is related to the temperature and strain with a constant of proportionality. These constant of proportionalities can be found out by doing the basic calibration constants, right? From that, we can actually detect where there is going to be some strain. And we know, based on the material behavior, how much is going to be the failure strain, at what point the material is going to fail. So because of which now I can have a confidence that, okay, if it falls within that range, my structure is safe. So this was the basic overview of what is optical fiber sensing. Now, basically, there are different types of optical fibers. So one is a point sensor, which is these days quite commonly used. One of it is called interferometric sensors. The other is the fiber Bragg grating. Generally, it is known as Bragg grating. These are point sensor, mean we will put it at the location which is most critical, right? So for example, this is our bridge, right? So in our bridge, this is my bridge pier, and I want to see the strain development at this junction, okay, the beam column joint. So I will put my sensors here. So I can choose what location I want to put, and I can send in the signals and I can measure. The other type are called the distributed sensors, because see, this was an example in which there is point failure occurring. But if you want to see something like a slope failure, I want to measure the strain development through this whole slope, whether it based on if it is an infinite slope or a finite slope. I want to measure what are the strains developed. So I can use this distributed sensors. So if you want to imagine these distributed sensors, they look like long threads, right? And this long threads, starting from location number 1 to say some 2 kilometers long, I can lay these optical fibers. And each point in this optical fiber, each and every point will act as a sensor. because I can capture or I can measure the strain in every, say, 1 centimeter of the distance, right? So it becomes highly accurate, the distributed optical fiber system. Although it is little bit expensive, we have to go for distributed optical fiber sensing for critical projects. So for example, in projects related to nuclear engineering, nuclear waste disposal sites, generally when we are disposing this nuclear waste, we will go deep into earth's surface, kilometers deep into the earth's surface. We'll create some containment systems, and in that we will be dumping this used nuclear fuels. So there we cannot afford any failure in this containment system, right? There we can use this distributed optical fiber sensors. Now, where can you apply um, um, this concept of usage of optical fibers? So one is dam. So if you look at this photograph, so this is a hill, and here you have a dam here, and from where water is stopped at this dam. For damage detection, I can use it. Here there is a slope. I want to stop failure, or I want to monitor the strains developed in this slope. I can do tunnel, very important, right? Because the type of dynamic loading that is happening inside a tunnel is very high. Also, if there is some catastrophe, the you can say the rescue measures are also quite difficult. So we can use this kind of system in tunnels to do the settlement analysis, in bridges, right? In levees, also in piers, as I told you, at the junction of the girder and the pier. For buildings, we can see for tall structures, especially now with the change, a lot of change in the building bylaws, we can see that with the coming high-rise buildings, the importance of damage detection or structural health monitoring keeps on increasing. And if we want to see the geotechnical aspect of it, we want to make sure that there are no unwanted settlements beneath this building, right? For pipe works, I have discussed about it. If there is any pipeline failure, we can detect using the optical fiber sensing. Then gas tanks, again, very important structure. So now to do this study, we did a small experimental, first of all, we prepared an experimental test setup, quite unique, because as far as I know, there were very few groups which we know were working on the usage of optical fibers in desiccation cracking, because we can use optical fibers in other known materials like concrete and other civil engineering materials like steel, because the prediction is quite easy, the material is known to us. But when we are using it on a material which is a non-linear material like soil, it becomes little tricky. So this was a unique test setup developed at Monash University, Australia, in which what we did is that we prepared the soil specimen. Okay, it was a huge task because this was a part of my doctoral work. In this work, I cannot change my soil type. I did some experiments in India and the soil was transported to Australia. The same soil was used to do the experiments. So linear shrinkage molds were prepared because desiccation cracking is happening because of the shrinkage. So we made the linear shrinkage molds and we allowed the specimen to dry, and generate cracks. So there was a weighing balance on which the specimen was placed, and the weight was recorded and monitored in a computer. Same thing, the specimen preparation, I'll just show you in the next slides how the specimen was prepared. But for the geotechnical aspect, we also wanted to see what is the effect of small reinforcing fibers that I added. So now we have to just keep this in our mind that I will be talking about two types of fibers. One is a reinforcing fiber and one is an optical fiber. So I wanted to see what is the effect of these small reinforcing fibers. So all of us have seen these small reinforcing fibers, generally Recron fibers are quite commonly used these days. The plaster work that we are doing on our houses, we don't want this plaster to crack. So we are using the reinforcing fibers, generally of polypropylene or polyester. So the same fibers were used for this test. So that was mixed with this clay material, and optical fibers were passed through the specimen and it was measured live. And the same thing, we had one digital camera on top of it to view the live images of the specimen. So these are the properties of soil that was used. It was a black cotton soil. We procured this soil near Pune, one of the location which is having high expansive soil. So if you look at the free swell index, it is more than 100%. Quite like high swelling soil. It was classified as CH. We did all the types of tests on it and ultimately classified it as a highly swelling type of clay. Right? The type of reinforcing fibers, three types were used: polypropylene, polyester, and polypropylene tape fibers. So tape fibers are nothing but the cross section will be like a tape. Cross section is like a rectangle, and the cross section will be trilobal. Here you can see the trilobal. What is the difference between triangle and trilobal? Triangle will have these edges sharp, whereas trilobal will have the rounded edges. So these are scanning electron microscopes or micrographs of the fiber used. You can see that the rounded edges are there, right? So first of all, lot of tests were done, basic tests to see the material characterization, right? So these part of tests were done in India to see what is the property of soil, what is the property of the fibers, that is geofibers, right? Mechanical fibers used. Then what is the property of the soil plus fiber? Then some tests were done. Then we wanted to do some basic tests to see whether addition of fiber is reducing the cracking or not. So a lot of tests were done, and finally we came up with this chapter number 4, which is nothing but the usage of distributed optical fiber system to find out the cracking. Now, to do the specimen preparation, first of all, what we do is that whenever there is a glass fiber, so here you can see this glass fiber, right? This is the glass fiber. We remove the top coating of it because we want to connect this optical fiber, which is passing through our specimen, to our data acquisition system. So उन दोनों को join करने के लिए, it is nothing but almost like soldering process that we do in electrical. So the same thing, we remove the top layer and then we will do this fusing by heating. So this is a heating fusion happening. Once this heating fusion is happening, the same thing is sent to the signal. So these are the optical fibers, and we will have a specimen here, which I will show in the coming photographs. This was our setup used, and we can actually in live we can view the strains getting developed in the soil. So if you want to look at the typical, so this was our sample, right? These were the linear shrinkage molds. One fiber will pass like this. So this is from the plan I'm telling. One fiber will pass like this. There was a loop made, and the second fiber, so it's the same fiber, but it is making two loops. And that is why you can see that there is a jump in these values. So this value and this value corresponds to this whole length of the sample. As soon as this shrinkage will be happening, you can see that the strain will keep on increasing. I'll discuss this in the coming slides. This is a schematic representation of the soil sample, as I told you. These are the linear shrinkage molds, 25 centimeter long, and it is having two holes were drilled, right? And optical fiber was passed through this whole setup, and then it was sent to this ODISI, which is nothing but our optical fiber system. So if you want to see schematically again what is happening, so for example, this is our specimen, right? Just imagine that these are the small clay particles which are coming closer and closer to each other. And there is a optical fiber which is passing through this, right? This optical fiber is making a loop and it is coming back. Now there is a light source. So as there is a light source, these small photon particles will be reflected, and the change in the frequency, that is the delta F, can be found out by the detector. It can detect the change in strain due to clay shrinkage, right? So this is the main working principle on the type of this optical fiber technique, right? So what we did, we prepared various samples, and these samples, they cracked differently. We changed the fiber length. This fiber is the reinforcing fibers, the small fibers that I have added. So on image number 1, that is A, it is unreinforced. It means it's a plain soil as is existing on the field. You can see that the specimen cracked at the center. Now for fiber L is equal to 6 mm, you can see that there is again a lot of cracking. For fibers, reinforcing fibers, L is equal to 12 mm, right? So if this is your sample, the fibers, the reinforcing fibers are like this, they're distributed in the whole specimen. Whereas, I'll change the ink color, our optical fiber is, our optical fiber is passing through like this. So if you see from the top, these are the photographs, there is no cracking in the specimen for L is equal to 12 mm. And also for L is equal to 18 mm. What is L? L is nothing but your cut length of the fiber, right? Now, this whole phenomenon, we all know that there will be a cracking, and to simplify this whole procedure, we chose linear shrinkage. Linear shrinkage means the specimens are very long. So it is expected that the sample or the soil sample will crack in the mid. So we are simplifying the number of variables, and then we are doing these tests. So when we are doing this test, just pay attention to this photograph. Now, first of all, look at the images at this C. Look at these images. At 0th hour means there is no evaporation, there is no desiccation from the soil. It means there is no change in the strain. there is no strain development. That is why the strain that you measure is 0. Now, there is slowly after 10 hours, what is happening? There is a loss of moisture from the soil sample, and because of this loss of moisture, there is some shrinkage happening, right? So this is our soil sample, and there is a shrinkage occurring. Because of this shrinkage, there are compressive strains developing in the soil. And the common, you can say the notation that is used in optical fibers is that the negative strain is the compressive. So slowly you can see that these graphs, they start showing some value in the negative direction, right? These, can you see the graph getting developed? It means the soil is undergoing lot of shrinkage. The soil will keep on shrinking, and at a point, this shrinkage is going to develop large tensile stresses in the body, right? It will keep on shrinking like a beam, right? There will be large tensile forces developed. So as soon as these tensile forces, they exceed the tensile strength of the soil, there will be a crack. Now, you look at the image number 30. So ideally, this graph should have gone like this, but suddenly at a point, you can see that there is a dip, right? This dip. And this dip is nothing but the location of your crack. So this crack location will show you at what point there is a crack occurring, right? Now look at the image number B. Here on top of it, I have placed the photograph of the cracking specimen. The soil will keep on shrinking. Here you can see the development of strains. The strains will keep on increasing. And at a point, as soon as there is crack formation, there will be a sudden dip that is seen here, right? Sudden dip at the center. And that point is showing your formation of crack. So in ideal case, what you can do is you lay your fibers in the soil and you monitor what is the strain occurring. And you know, by doing some basic tests, you know that there will be a crack developed at this much strain. So if you see that this much is happening, you can do some remedial actions. So for this kind of, you can do some re-wetting of the soils of the layer, or you can take different steps. Or if it is an application like slope stability, you can give an alarm to the residents of that area that okay, this may fail soon. Just like we use satellite images to detect any kind of damage, right? Now, what we did in this experiment, we wanted to compare the cracking in a plain soil with the reinforced soil, these small reinforcing fibers. What happened in the case of reinforcing fibers? Now you look at it. So these are the fibers. This is the soil sample, which is reinforced with small fibers. So if you want to look at this in a micro, like I want to magnify, what will happen is that these are small reinforcing fibers which are sitting in the soil matrix. There will be, I'm expecting that there will be a crack which is propagating in this direction. Now it may come across a fiber here, and because of the presence of fiber, this crack propagation is stopped, right? again there will be a crack which is propagating and it will be stopped here. Similarly, everywhere there will not be a huge crack like we saw in the unreinforced soil. In unreinforced soil, we saw a huge crack like this. In this, we will find micro cracks. And these micro cracks can be measured in optical fibers. I'll show you how beautifully that is captured in the optical fibers. So look at the 0th hour, no strains. At 10th hour, again, there are some strains. 20th hour, there are some strains. 30th hour, there are some strains. 40th hour also, there are some strains. 50th hour, there are strains. But if you look at carefully, there is no abrupt failure like we saw in unreinforced. It means there are small dips. There are small release of strains because of these micro cracks which are caught by the optical fiber. So this actually helps us in understanding the physics behind the reinforcing fibers, that it helps in mobilizing the strains in a very small strains, right? And the whole sample is held intact. There is no abrupt failure. And that is how we try to compare these two things with the help of the optical fibers. So the same thing was projected on a contour map. If you look at the image number A, I'll go back to the slide where I showed the unreinforced specimen. So these are this contour map actually shows how the failure pattern or the strain contours in case of unreinforced soil, they developed with time. So this is 0, 10, 20. These are the time is increasing in this direction. So you can see that as the time increases, at the center, there is an increase in the strain value, right? So this maximum values can be seen here. These values, these point, right? So this unreinforced specimen acts like a beam. What happens to a beam? So for example, if this is your beam, at the center, this will crack. And as this cracks, it will become like one is this part, the other is this part. These are two separate parts. And again, this separate part will keep on shrinking. And those cracks, those strain development are seen here. And again, there may be a point where this will also crack, right? Same thing is seen in the case of micro cracks, right? So, but there is no abrupt cracking that is seen. And all of this in this study, what we did is that all of this was also recorded with the help of a digital camera. So this strain development, strain is nothing but delta L by L, change in the length due to shrinkage by the actual length of the specimen. So this delta L by L was also plotted for the images. Using image analysis, we did. But although there will not be a correlation between these two things, because the image analysis is measuring something from the top, and in this, we are measuring the strain development within the soil material. So there will be some, you can say some correlation, but it will not be same, right? So if I want to actually measure and I want to tell like what are the main inferences that I can say from this is that I can tell that the strain required for first crack, for crack initiation is low in the case of unreinforced specimen, right? This one. So this is 0. Please mind well that we are going in negative direction. So at a very low strain values, very low strain means at a very low shrinkage, I can expect an unreinforced specimen to crack from the middle, right? When I'm using some fiber reinforcement like 6 mm fibers, 6 mm fibers are very, very, very fine, right? 6 mm is like, you can imagine it's half of 1 centimeter. So these are very fine. So they may not resist the cracking. That is why the crack value is almost similar to the unreinforced specimen. Whereas when you use 12 mm reinforcement, the amount of strain required for first crack is quite high. It is very high. It's about, you can say, 50% higher than the unreinforced specimen. The same thing, 18 mm you're using, it is also showing a higher value, right? Now, for the second crack, as I told you, like the specimen, it cracks from the center. So this is in part number 1 and part number 2. This part will again try to shrink, and that will undergo some cracking at its center. So this second crack, the amount of strain required for the second crack will be very high. Why will it be high? Because since the length has reduced, the shrinkage will reduce. That is why the tensile stresses developed will also reduce. So to make it crack, it has to take a lot of strain value to undergo the cracking, right? So from this, during the cracking, entire soil specimen is experience a compressive strain. First of all, we have to like remember this thing. And these compressive strains are developed, these actually are causing the tensile stresses to develop, and they will cause this tensile crack formation. And the compressive strain profile that is developed in a fiber reinforced soil, you can say that it is less undulated. As I showed you in the previous photographs, there is a less abrupt cracking because of that, right? When it is compared with unreinforced soil specimen. The micro cracks, which are helping, these are the small points of stress failure. So you can just like relate it to our daily lives. So if you have an office job, what do the health experts tell you? Like, you don't have to exercise like for 1 hour every day. Instead, if you're having a office job, you just stand and you reduce your stress. You stand for a while, take small breaks in your whole routine, and that will help you to reduce a catastrophic failure. And that is what these micro cracks are doing, right? The fibers of length 6 mm, that is very fine fibers, they were found to be too short to restrain cracking. They got pulled out at the uh, width of the crack, as I showed you in the previous photographs. And also, the soil specimens that were reinforced with 12 mm, they were found to possess a highest compressive strain. And that is how we can tell how the crack can be delayed from this whole exercise. So this was a unique experimental test setup, and this was just a beginning. And this work was taken forward by our research group. So our research group also works like in Monash University on the pipe failure detection, right? Because in Australia, there are mostly cast iron pipes, which are being laid. Old pipes are there, and these pipes are of critical importance. We don't want them to fail. So optical fibers were laid on these pipes, and the strain are measured, and the damage is detected. If there is some failure which is going to occur, it is alarmed, right? So other kind of examples are that this can be applied to the optical fiber sensing technology can be, first of all, used in physical modeling. all of us know that in civil engineering, how important it is to do some physical model tests, because see, our structures are huge. We cannot depend on field data. We want to do some small scale, laboratory scale physical models, and we want to measure things. And to use methods like optical fibers, our data becomes very rich, because we are capturing data at each, like every second, we can get the data at a very, very small intervals, and we can study about it. So I hope all of you enjoyed this talk. I tried to keep it as generic as possible so that every one of you understands it. And please contact me at the given email ID if you want to like ask any questions, or if you want to collaborate. So I'll be very happy. We have a small research group already formed in PDEU Gandhinagar. We have a couple of MTech students, a very active group of BTech students with us, who have started to work on various kinds of soil stabilization techniques. It can be physical stabilization, it can be chemical stabilization. I'll be very happy to collaborate with any one of you in any kind, if you want to do any internship or any kind of collaboration work is highly welcome. So please write to me if interested. So I welcome the questions, and over to you, Siddharth sir or Aditya sir.
Okay, madam, it was really nice presentation, very lucid presentation, I must say. So very first question is from Professor B. A. Mir, and he wants to know that expansive soil is highly compressible with MDD around 12.5 kilonewton per meter cube, but UCS is of 200 kilopascal. So soil is too high and mismatching with this index property. What is your comment?
The soil, the UCS, because it's a very stiff, sticky type of stiff clay, and that is why we found the UCS values to be very high. Although this MDD value was not used in this experimental test, what we did is that because we wanted to see the maximum shrinkage, we prepared the specimen at its respective liquid limit. So the liquid limit came out to be close to 100. So we mixed the specimen at that, and we prepared a slurry out of it, and then this soil specimen was allowed to shrink, and then we took out the values of this shrinkage, and the same thing was compared with the optical fibers.
His question is MDD was very less, I guess. MDD is 12.5 and UCS is 200 kilopascal. But you said that your specimen were casted at liquid limit. So there was, because it is a black soil, so it may give very high cohesive value when it's dry, right?
Yeah.
Okay. Next question is from Deepa Iyer. Can optical fiber be laid in unidirectional only, or we can lay them in bidirectional?
Absolutely, it can be placed bidirectionally. We have problems like you can say slope stability, or you can say in problems like pavements, or any kind of dams, where we want to see both the failure in the X direction and Y direction. It can be placed like a grid. So there are some papers which actually discussed about the laying, that you are saying that in what pattern we can lay these fibers, or if it's a distributed optical fiber, we can lay it, or if we are using the point sensors, at what locations we can place these point sensors. There is a good, very nice paper on it. Please, if you want, I can share that paper with you.
So one doubt I have, that these optical fibers are made up of the glass, and
Yeah.
you are working at very low strain in micro strain ranges. So, I mean, what is the strain level that can resisted by these fibers, and in what case it will fail?
Um, so as per my observation, the I have shown the in the previous slides. So this is the strain resolution. It means at 1 microstrain, till 1 microstrain, it can measure the soil, the
Oh,
glass fiber. So 1 microstrain is like extremely small value, because if I look at this sample which is getting cracked, it gets cracked close to say 2000 microns, right? So the first crack you can say is occurring at close to 2000. There was a shrinkage of close to 20 to 30% linearly. And after that, for some specimens, we observed that this optical fiber, it broke, like you said, like there will be some maximum limit to it. But since this was for just experimental purposes, we did not apply, or we did not jacket this fiber. In the field, what we do is that these fibers, they are not barely, they're not placed bare in the soil. We have a jacket on top of it, because the strains are even further high. If there is some like some deflection or large amount of strains, when we want to study, different types of jackets come up. And there have been some studies in which the effect of the coating or the jacket, how much it is going to give us the change in the strain value, is also discussed in those papers.
then there is one more question from Deepa itself. Is there any sample preparation method particularly to insert optical fiber in soil sample?
Yes. So when we are working on soil, the first and foremost important thing is that we want to ensure some kind of um, adhesion between the fiber and the soil. Because see, if this is my fiber and this is the soil matrix which is around it, and if there is no adhesion between them, it will just slip. The values that it is giving you are false. So for soil, it becomes little tricky. So in normal life, generally we see the soil which is at close to plus or minus of its liquid limit, or it is at least in its plastic state. So there is a binding. So in my experiments, when I started the tests, the values, it was giving some abrupt values, because the soil is like a slurry. So as you asked me, is that first of all, when we are laying these optical fibers, we have to make sure that if the soil is very loose or it is like a liquid, you have to wait till it reaches or it enters into the plastic phase. The values that you are getting there are not accurate. So sample preparation, first of all, that thing needs to be taken care of. And next thing is in what direction you are laying the fiber, or what is the specimen size. Because if the specimen size is too small and you are laying these optical fibers, this optical fiber itself will resist some cracking, right? So that also needs to be taken care of when we are using materials like soil. For other materials, like some people from our research group, they were studying on beam failure, for example. It was little easy for them, because material is known. You can lay the fibers within that material, and there will be a good adhesion ensured within the fiber. Also these days, different kind of people are using resistors. So for example, if this is my fiber, I can actually place some kind of beads along this fiber. So this bead will act as a point so that there will not be any slippage of this fiber through the soil sample. So I hope I could answer your question.
Okay. Next question is from Devanshu Chaglani. Has optical fiber application been practiced in any of the project or documented in India? Can you kindly show the same if it is?
I'm sure the optical fibers have been used in different projects, although not very widely been used. Distributed optical fiber sensing, I doubt, but the point sensors that I'm seeing, the Bragg gratings, have been quite actively used in some applications, especially in tunneling. Right. I don't have the data as of now. If I find it, I will surely share it with the organizers to share it with you.
So, any more questions from participants? There are questions here. How displacement is measured by using fiber sensors in bridge?
Okay, so like in bridges, um, the same concept can be understood. I'll just go back to the old slide where I mentioned. I hope my screen is visible. I just clicked on stop sharing.
No, it's visible.
Okay. Any concept or any measurement because of this optical fiber sensing is based on this very easy concept. Like if there is a bridge, just imagine that your bridge is like this, right? This is your bridge. This is your shape here, and you have some vehicle which is flying over it, right? And you have an optical fiber which is laid through this bridge. There will be a light source here. This light is sending here that there will be some signals. In a normal typical case, as soon as a vehicle moves at this point location, there will be a strain developed, and this strain will cause a change in the frequency, and that frequency change can be caught. It can be recorded by our detector, or you can say the receiver end, right? Now in bridges, what we can do is that it is undergoing a lot of dynamic action, right? There will be vehicles moving on and on and on. So there will be always some strain measured. But by calibrating, you can set up a value like after this point, there may be a crack formation at this location. If there is no proper reinforcement, or you can imagine any cause of the failure, but if there is a strain which is getting detected above our critical limit, we can alarm that this may fail, or there may be a failure which is going to occur, or this is undergoing some kind of damage. It needs some retrofitting. So I think I was able to answer your question.
I have one small doubt that what would be the maximum length of this optical fiber, because you are emitting one light source and which will be received by the end. So there must be certain frequency limit, or because certain frequency will die out due to damping maybe, or I'm not sure. So are you getting my point that
Yes, yes.
how long
Um,
should this optical fiber, or If it is long, then can we increase the intensity or frequency of the emitter?
Yes, sir. So first of all, the main advantage here we have is that these optical fibers. So this is the same optical fibers which come to our house, for example, for say TV signal or any. So these are laid for kilometers long, like hundreds of kilometers. It can transmit,
Minimum damping, right?
right? And we are depending on light signal. So light signal, again, there will be minimum damping as you measured, there will be minimum loss within that glass. So we can go for extremely long lengths. So for plane strain conditions, like plane strain condition problems, as in whenever we are talking about canal linings, or we are talking about long projects or infinite slopes, or critical importance, like containment systems, we can go for a very, very long optical fibers, and we can do the damage detection. That is the main advantage here.
Correct. Okay. So I think we have received. What is the reason behind the cracking occurring at the middle point and not anywhere else?
Yeah. So I'd like to explain this with the help of a small. So this is a plain page. I'll do that. So what I wanted to do is I wanted this material to crack at a location that I know, right? Because that will simplify my problem. If I took a circular specimen like this, there can be crack here, it can be crack anywhere. Whereas if I make linear shrinkage molds, what will happen? There will be a shrinkage which is going on in both direction. The soil will shrink like this, and there will be maximum strain which is developed at the center. And then it cracked at the center only. So this, you can imagine it like a simply supported beam. What happens to a simply supported beam? So if it is a classical simply supported beam, it will fail at the center. So that is what was aimed, that it should fail at the center, so that I can reduce my variables and I can do the analysis easily. Right? So although I used optical fiber which is distributed throughout the specimen, there are some papers in which they made this shrinkage molds and they used point sensors. Like they placed this sensor only at the center. They know that there is going to be a crack which is going to occur only at the center of the specimen. You can record it. Of course, if I wanted to make this more interesting, if I wanted to make this as a 2D problem, I can choose a sample like this, and I can lay a grid of optical fibers and see how the crack is getting transmitted or propagated throughout this whole specimen. Right? I hope the question was answered.
Correct. Any more questions? Yeah, I think people are satisfied now. So if there are no more questions, then we can conclude. Any questions? Last chance, participants. Okay. So can you stop sharing your screen, ma'am?
Yes.
So thank you, ma'am. It was really very nice and lucid presentation. So you are a good teacher, and that is reflected by your presentation, right?
Thank you very much.
So thank you very much for your time, energy, and expertise which you have shared to our audience. and definitely our audience and in fact few of our students would like to collaborate. If they are interested, we'll definitely be in touch with you, right?
Thank you very much. And I think the feedback was really encouraging. Thanks a lot.
Thank you, thank you. And for the participants, next speaker we will meet at 2:15. So we take a lunch break, and he is Dr. Sharnil Pandya, and he is an official IBM IoT trainer. So at 2:15 we will meet sharp. So we end the meeting over here. Thank you, Uma Madam, once again. Thank you all.
Thank you very much.